let's start what we have not finished last Friday. And the last part for self-supervised learning is I would like to share with you how to apply self-supervised learning on speech processing. And I really want to share with you this part. I know I also need to talk about meta-learning, but even though we do not really finish meta-learning, it is fine. I have the recording for the whole tutorial. So if I cannot finish the lecture, I can share the recording with you. It's the recording given in the conference. And so for this part, I'm going to talk about how to apply self-supervised learning for speech processing. And I know many of you already have your research direction. You already know you want to apply machine learning in which application, because besides technology and theory, you also need to apply your technology on some application to show that the technology you develop is very useful. And probably some of you have not found an application you want to apply. So I would like to talk about how to apply self-supervised learning on speech. Probably this can inspire you to working on speech processing. So self-supervised learning, we already introduced its framework. The same framework can be directly applied on speech processing. So we have pre-training. So you have unlabeled data. You can train an upstream model. And this upstream model take the speech signal as input and output a sequence of representation. So just like how you apply upstream model in natural language processing, for example, bird take a token sequence as input and output sequence of representation. In speech, the upstream model would take speech signal as input and output a sequence of representation. And there are many ways to train this upstream model. Here, I just list few of them, and I'm not going to go through the detail here. One thing I would like to emphasize is that those pre-trained methods, they are task agnostic. So in phase one, when we do the pre-training, we do not know what downstream task will be. And this is one way to pre-train your model. And we have introduced BERT last Friday. So the same idea can be directly applied on speech. So the idea developed in natural language processing can be directly applied here, and it is helpful. So this is how you apply the idea of BERT on speech. So in BERT, you mask some token. In speech, you mask some span of signal. So given an utterance, then you mask some part in the utterance. Then you can train a model, the model output the representation, and you have a linear classifier. You have a, I should not say it is a classifier, because what we actually do is regression here. You have linear layer, transform the representation into the mask signal. So you have to reconstruct the signal, which is masked. And we call this model Monkey J because it wants to mimic the input. It wants to repeat the input. It has nothing to do with Hungry Gen. And besides Monkey J, there are a wide variety of different ways to train your self-supervised model. So in our speech community, there are already lots of different self-supervised models. There are already lots of speech version of BERT. Okay, so they are trained in different ways. I'm not going to go through the detail here. Then you can apply this upstream model you can apply this self-supervised model in your downstream task. Let's say you want to apply this model in ASR, in speech recognition. So ASR is speech recognition. So I believe you are familiar with this technology. The model has to take audio as input, then output the speech transcription. And you have a little bit label data. You have utterance and its manual transcription. And you have a downstream model. The downstream model take the representation as input and output the transcription, output the speech transcription result. and you use the label data to train your downstream model. And perhaps you can also use your label data to fine-tune your upstream model. So this is the basic idea, what you do in the downstream task in speech processing. And here I have a question. We already have a wide variety of models, those upstream models, and they seem to work very well on speech recognition. However, speech recognition is not the only task related to speech processing. When it comes to speech processing, usually people think about speech recognition, but I would like to tell you that speech recognition is one of the tasks in speech processing. Speech processing is a very wide area. We have lots of different applications. So is this model specialist for ASR, or are they universal? To be more specific, what I mean is we have an upstream model. We can use it in speech processing. We can use in ASR. ASR means automatic speech recognition. We can use it in speech recognition. Can it also be used in other applications? For example, speaker identification. In speaker identification, what a model needs to do is, given an utterance, it has to determine this utterance is produced by which speaker. If a model already achieved good performance on speech recognition, can it also achieve good performance on speaker identification? If you asked me this question several months before, I would say I believe those models are specialists. They probably can only solve the task related to speech recognition. Probably they would not work well on speaker verification or speaker identification. This is because speech recognition and speaker identification, they are kind of very different tasks. In speech recognition, what your model have to do is to ignore the speaker information. You know, different people say hello, the signal is very different. So the model have to learn how to ignore the speaker information to achieve good speech recognition performance. On the other hand, for speaker identification, your model have to tell the difference between the speakers. It has to learn the speaker characteristic. It has to ignore the content information. So speech recognition and speaker identification, they are very different tasks. The model can work well on ASR, probably cannot work well on speaker identification. So this is my 2 cents several months before. But let's still do some experiment. So here we have a benchmark corpus called Superb Speech Processing Universal Performance Benchmark. So this project includes lots of different institutes, include National Taiwan University, CNU, MIT, Johns Hopkins, Facebook AI, LXT, and Hugging Face. We also publish a paper in InterSpeech. So if you want to know more detail, please refer to the InterSpeech paper. In the past, although in speech community, many different institutes working on self-supervised learning, but we do not have a benchmark corpus. In NLP, as I have told you last Friday, there's a corpus called GLUE, and everyone evaluate their supervised model, self-supervised model on GLUE. But in speech, we don't have that benchmark corpus. So this is why we want to have a benchmark corpus like GLUE. So now we have Superb. It can be considered as the speech version of GLUE. Then in Superb, we are going to apply a wide variety of different models on many different tasks. So besides ASR, automatic speech recognition, we are going to apply the model on many different speech-related applications. So this is our contestant. So this is the self-supervised model we are going to evaluate. I'm not going to go through the detail of this model. So you can formulate those models lots of people working on this direction. So there are already lots of different self-supervised model for speech processing. There are already lots of different speech version of BERT, and they are trained with, they have different network architecture trained by different corpus. And here I also try to summarize the training methods. And we found that they are, in general, 6 different ways you can apply to pre-train your model. And those models are usually trained by the combination of some of the approaches. But we do not have time to go through the detail today. Just want to, you just have to keep in mind that there are lots of different approaches to train the self-supervised model. The masking approach, like BERT or Mockingjay, is just one of them. There are other different approaches not mentioned today. So here I'm going to share with you the task we are going to evaluate. And this can give you an impression that speech has many different related tasks. We have many related tasks beyond automatic speech recognition. So let's start with the task related to content information. For example, you can do phoneme recognition. It's also related to speech recognition, but simpler. So give your machine an utterance, it have to output the phonemes. Then we have keyword spotting. So you say a keyword and machine have to know which keyword you say. You alter which keyword. And we have speech recognition, of course. This is the most difficult one. And we have query by example. What is query by example? Query by example means you have a spoken document, for example, a recording of the lecture, which is several hours long, and you want to find some important information in the lecture or in the news recording. Then how can you do that? Because an lecture recording is very long, several hours, and listen through all the material is very time consuming. So you can search through the spoken document automatically. So in query by example, you provide a spoken query. For example, you want to know what is superb, but you do not know in which part of the lecture mentions superb. So you just say superb, you provide a spoken query. And hopefully, a query by example model can identify all the region that superb is mentioned in the lecture. So this is the task related to content. We also have tasks related to speaker. We tried 3 tasks. One is speaker identification. Given utterance, the model have to determine this utterance is from which speaker. We also have speaker verification. That is given 2 utterances. The model have to determine the 2 utterances are from the same speaker or from different speaker. Speaker identification and speaker verification sound similar. They have a similar name, but actually they are different tasks. And we have speaker diarization. So speaker diarization means you have a meeting recording and there are several speakers in the meeting recording, and sometimes they will even say something simultaneously. And your model have to know that in this part, A is speaking, in this part, B is speaking, in this part, A, B is speaking simultaneously. So this is speaker diarization. We also have semantic related tasks. We have intent classification. Let us give an utterance. Your model have to identify the intent of the speaker. We also have speech spoken slot filling. Let us given an utterance. For example, I fly from Taipei to New York, and the system have to extract the information. It have to do slot filling based on the speech signal. It have to know that your from location is Taipei and your destination is New York, something like that. Usually, typical way to solve intent classification or speech slot filling is you have a speech recognition. And you have a speech recognition model to first transcribe the speech signal into text. Then based on the text, you can, based on the transcription, you can have a natural language processing model which try to understand the transcription result. But here we have an end-to-end model. Our model directly takes speech signal as input and directly output the final result, directly output what we want, directly output the understanding result. We also have emotion task. So given an utterance, we have the classification result, which is the emotion of the utterance, for example, happy, angry, or sad. So let's start again. In round one, we have some constraint to the self-supervised model. Our constraint is we fix the upstream model, and the downstream model only take the last layer output from the upstream model as the input. You may ask why we fix the upstream model. Fine-tune model probably will give us better performance. Yes, we have tried that fine-tune model can give you better performance. But what we want to verify here is what would happen if we just fix the upstream model? Can we get good performance even though we do not fine-tune the upstream model? This is what we want to verify. And we try to keep the network architecture of the downstream model as simple as possible. And this is the model architecture we use in the downstream model. And you can find that in several different applications, in several different downstream tasks, we can simply deal with it by linear model. Even though there are some very sophisticated tasks, for example, speech recognition is pretty sophisticated. Usually you need, for example, more than 10 layers of network to deal with it. But here we only use 2-layer LSTM. So and for slot fitting, the model not only have to do speech recognition, but it also have to do understanding at the same time. But we only use 2-layer LSTM as the downstream model. We try to keep the downstream model as simple as possible. And you may ask why we have this constraint. The reason is we want to use one upstream model to solve different tasks. Because the parameter of the upstream model is always fixed, it does not fine-tune corresponding to the downstream task. It is always fixed. That means we use one upstream model to all the 10 different tasks. We do not fine-tune the upstream model to fit the downstream task. We do not design the upstream model to fulfill the need of downstream tasks. This upstream model can be something off the shelf. It is good for all the different tasks. And because the downstream model only have very limited capacity, we try to make it very simple. And so they have very bad capacity. So we need to rely on the upstream model to achieve good performance. If in this constraint task, fixed upstream model and very limited downstream model, we can still get good performance on the downstream task. That means the upstream model can extract universal feature. It can extract a set of features which is good for all the different tasks. In this case, if in the future you want to build a new application, you have a new downstream task, probably you can simply use the upstream model. This can be an off-the-shelf model. You do not have to fine-tune it. You directly use this model in the new application. This sounds too good to be true, but anyway, let's do some experiment to see what would happen. This is the experimental result. So here, the columns, each column represents a task. So we have 4 content-related tasks, 3 speaker-related tasks, 2 semantic-related tasks, and 1 emotion task. And each row represents a self-supervised model. So we have many different ways to train the self-supervised model. So we show the result of each model here. And F-bank is the result without self-supervised model. So F-bank is one way you represent the raw speech signal, and it is widely used in the previous work. Some people may have heard NFCC, which is another feature. but based on my survey, FBank is more popular than NFCC in the recent year. Okay, so FBank is a widely used way to represent speech, but it's handcrafted feature. And here we have a set of self-supervised model. We have a set of upstream model. And there are many different numbers. And so it's not easy to interpret this table. And for some number, it's higher the better. For some number, it's lower the better. And they are not all of them are accuracy. Some tests have their own very special evaluation metric. So to make you interpret this table easier, here the black box, the answer, the number in black box means its result is worse than FBank, means the upstream model is not helpful. And we can find that the upstream model is helpful in many different cases, but it looks like the upstream model are struggle in some tests like ASV. This is speaker verification, automatic speaker verification, and SF. This is spoken slot feeding. There's still some tests which make the self-supervised model a little bit struggle. And we do not show the result of large model. So here we only show the smaller wave-to-vec model and the smaller Hilbert model. This is because we found that large model actually perform poorly in round one. So it looks like in round one, we do not fully leverage the power of self-supervised model. So we have round two. In round two, we still fix the parameter of upstream model. We still keep the downstream model as simple as possible. The only thing changed is we do not use the last layer, because we found that in an upstream model, each layer can extract different information. We found that some layer extracts speaker information and some layer extract content information. And usually the last layer is not the layer contain the most information. So if we only take the last layer, we cannot fully leverage the power of upstream model. But as I mentioned, different layers extract different information, and different downstream tests need different information. So how could downstream model select the layer? So this is the idea. So we have mentioned this idea when we talk about ELMO last time. So I have mentioned several different ways to leverage the self-supervised model. And I have mentioned that one way to leverage your self-supervised model is take the representation from all the different layers. So we take the representation from all the different layers, and the representation from all the different layers are weighted sum. And the downstream model take the weighted sum result. We take the result of weighted sum as the input. And the weights are learned with the downstream model. So in each downstream test, the weights will be different. The self-supervised model is still fixed. We still fix the parameter of self-supervised model, but the weights for each layer can be changed based on the downstream test. In this way, the downstream test can select the layer which contain the useful information for the specific downstream test. So this is the basic idea. And here is our results, and we can find that in the round two, there are less results which is worse than FBank. So in round two, in most cases, self-supervised model can outperform FBank. So this is the result in round two. We also found that there are several self-supervised models which are all around. And so NPC, Decora, Wave2Vec series, and Hilbert series, they are better than FBank in all the 10 different tests. It shows that those self-supervised speech models are all around. They work well on all the different tests. So the result is different from what I was expected. It looks like those models are universal. even though speech processing include wide variety of different tasks, speech recognition, speaker identification, they are very different tasks. But some models is universal. Some model can solve all the different tasks. Then the question here, but I do not have answer at this moment. The question here is the pre-training is task agnostic. We train those self-supervised model in an unsupervised way. They usually train by an auxiliary task, for example, masking the input, try to recover the mask input. The training process is task agnostic. The self-supervised process, the pre-train process is task agnostic. Then how can this upstream model become universal? I do not have a very good answer at this moment. And if you are interested in Superbenchmark, if you are working on self-supervised model for speech, or if you know any of your friends working on this direction, till then, we have a benchmark here. We have the Superbenchmark. It is online. You can submit your own result to the Superbenchmark to see whether you can achieve the state of the art. And recently, this is what our leaderboard looked like several days before. So recently, Microsoft just submit their result. It looks like the WEF LN achieved the best performance. It looks like WEF LN is the SOTA at this moment. And welcome to submit your result to this benchmark. And we have a workshop for self-supervised learning. The deadline is extended. The deadline is today, but it's AOE. The deadline is everywhere on earth. So you know any friend working on self-supervised learning, tell he or she you still have 24 hours to submit the paper. And if you know anyone, if you and or your friend is working on self-supervised learning, welcome to submit to the special issue of self-supervised learning for speech and audio processing. The deadline is the last day of this year. Okay, so this is about speech processing. Okay, so let's see whether the audience have some question. So here, Manish have a question to follow on from Oscar. Can you comment on how we can generate sympathetic data? Okay, so we can design how to generate sympathetic data by ourselves. The reason we use sympathetic data to train our model because we want to know what is the factor that influence the performance of self-supervised model. So we try to synthesize the data in different way. You can invent your own way to synthesize the data. At the very beginning, our ambition is probably we can develop some very smart way to generate the data, then we can achieve the performance as good as training on English data. But unfortunately, until now, we still cannot find a very good way to synthesize the data so we can obtain the same performance as training on English. However, we still learn a lot from the process. So I would like to summarize it again a little bit. So if you random generate your data, it doesn't work. And if you generate your data by some sympathetic structure, it works. But then we found that sympathetic structure is not the reason you get the performance. If you can generate your data and let your model can have a wide range of attention, that is the task need to be solved by go through the whole patterns, this is maybe the reason you can get the performance. But this is still something under investigation. So this is a very interesting research topic. You can try to develop your own data generation approach and to see whether you can get good performance. I found that Wei-Sun have a very good question. Do the methods they are universal have common property, such as similar architecture or self-supervised laws? This is a very good question. actually they do not share common property. So here, NPC is masking approach. So it's developed by an NIT student. He was also an NTU student before he joined NIT. This is a masking approach. The Cora 2.0, to my best knowledge, it also tried to recover the masking part. Web to Vec is contrastive approach. So it tried to make some positive example, their representation close to each other, and make negative examples separate. And Huber is another interesting approach. It is either reconstructing the mask input or contrastive approach. It is completely a different approach. It's we cluster an FCC and try to make some pseudo label, and it trained to predict the pseudo label. This approach, at the beginning, I don't think it will work well, but anyway, based on the experimental result, it's super good. So they are covered wide variety of different approach, and all of them can be all around. So this is something very interesting. We still haven't recovered what is the mechanism to make those models all around. But there is something under investigation. We found that, as I have mentioned, each layer includes different information. For example, we found that usually in the first few layers, it includes the speaker information. In the last few layers, it includes the content information. And this is probably the reason why the model can solve different tasks, because its layer contain different information. And if you can make your downstream model select the proper layer, you can solve a wide variety of different tasks. But the mechanism why model can achieve that is still unclear. So thanks, Wilson, for a very good question, but I do not have a good answer at this moment. The superb test for adversarial cases? The answer is yes. This is a future work we are working on. So I will answer your question. I will answer Chang Kai Chen's question in a few minutes, after a few minutes. So if you do not have other questions, let's go forward. So now we see a new paradigm. This new paradigm is we have a fixed upstream model, and this upstream model can be used in a wide variety of downstream tasks. As I was mentioned in last Friday, this upstream model can be a utility. It is provided by big company. It is something like Android. And all the individual, small company, school lab, we can leverage the upstream model to do our own application. So we have seen a new paradigm. But the new paradigm lead to new risks. One is everyone knows that adversarial attack is something very risky. In the future, if all the different application is built based on the same upstream model, then the attacker only have to attack the upstream model, then it can broken a wide variety of different downstream tasks. Is this a true threat? We already have some investigation. We already tried to use adversarial attack to attack the upstream model. And we found that in the white box case, it's very easy to attack the upstream model. Then after you attack this upstream model, then you can broken all the downstream tasks in Superb. But on the other hand, in black box attack, we do not achieve a very good performance. The adversarial attack do not work well. Probably this is a fortunate thing. Adversarial attack do not really work well in black box setting on Superb. And this is still something under investigation. Then we have privacy issue. The upstream model will be trained from a large amount of unlabeled data. So you can imagine that in the future, Amazon will probably collect the data from the customer, and when you talk to Echo, your speech will be used to train an upstream model. The upstream to train an upstream model, we do not need label data. So collecting those speech from the assistant probably will not violate the policy because no one really listened to the speech and have the labeling. And you can always delete the utterance you store on the cloud. So you can always delete something you do not want to be stored. However, if this upstream model is public available, if it is an utility, and this public upstream model is trained from some privacy data, even though those data is deleted, even though this data is not public available. If upstream model is public available, can someone do reverse engineering to recover those privacy data? So this is probably something very risky. But fortunately, we have not figured out a good way to recover the training data from the upstream model. And probably we also have to consider the bias issue. So upstream model is trained from unlabeled data. So no one can go through those data to check what upstream model have learned, what is included in those unlabeled data. So it is possible that those unlabeled data has some bias. Then the upstream model learns some biased information. In this case, if our labeled data is balanced, can we still have an unbiased result? Or if upstream model is already biased, then we can never correct it by downstream model. This is still something under investigation. And I add one more slide because on last Friday, several people asking the question about network compression. So I add this slide to tell you that there are already lots of research trying to compress the self-supervised model. And I put a link of reference here. Someone already collect a large amount of paper about network compression to self-supervised model. And if you want to learn more, I put some keyword here. You can Google distilled bird, tiny bird, mobile bird, Q8 bird, and L bird to learn more from how to compress self-supervised model. So anyway, a new era for self-supervised learning is coming. So this is the information I would like to share with you. Okay, so this is for self-supervised learning. So if you have any question, you can type in the chat room and I can see it immediately. So if there's no further question, let's move to Metalearning. Okay, I found a question here. While we are opening the slide, let me read the question. Okay. Oh, here we have a very long question. The question is, this is an extension of my question from last class regarding rotating distribution. If we assume that learn distribution of different data sets just need to be rotated to match each other, then does that mean that semantic meaning of embedding distribution are rotationally invariant? In turns, does that mean learning relative differences via clustering or contrastive learning lead to the most natural embedding distribution rather than caring about labels? Let me try to answer the first part of your question. So your first part is are the embedding distribution rotationally invariant. That is, you can rotate the embedding of one language and obtain the embedding of another language. Actually, this is pretty much the truth. So you can Google one thing called MUSE, M-U-S-E. You can Google MUSE. This approach is unsupervised learning, the embedding representation of different languages. That is, you have the representation of English, you have the representation of Chinese. Then you can learn a linear transform, and this can be learned in an unsupervised way. You can learn a transform and apply this linear transform on English, and it is transformed into the space of Chinese. Then you can automatically align English and Chinese together. And in this way, unsupervised machine translation can be achieved. And you can read the paper, and surprisingly to find that in some languages, unsupervised translation can almost be as good as supervised learning. So you can read the paper of MUSE, and from that paper, you can find more following work. Then the second question is, does that mean learning relative difference leads to the most natural embedding distribution rather than caring about label? I'm sorry that I do not really get this question because I do not really know the definition of natural here. I mean, different tests need different representation. So if you have some label, so if you want, so for example, in speech processing, if what you want to do is speech recognition and your label is content, you want to transform utterance or audio speech signal into content. Then you can find that in each layer, the content information, the information not related to content, for example, speaker information or noise in the environment are gradually removed in each layer. And is this unnatural? I do not really know the definition of natural here. I think this representation is exact for deal with the problem you want to solve. So if what you want to solve is speech recognition, it is good to remove those speaker information or environment information not related to the content. Natural means how a human being might group the same labels in a mind map. Okay. I kind of get your question. I do not really have a very good answer at this moment. Let me share with you more information. So let's say so now what we want to do is collect lots of unlabeled data and use those unlabeled data, unlabeled speech data to train a model. Hopefully it can automatically learn a language. This is something very similar as what baby do. However, if you only consider the acoustic signal and some terms, some phoneme, they are very close to each other. If you only consider the acoustic signal, they are not separable. For example, light and right. Light means something bright, okay? Right is left and right. They are very similar. L and R, they are very similar. If you only consider the acoustic, probably they should not be considered as two different phonemes. However, the English native speaker baby, they listen to lots of English sentences, English utterances. Finally, they will find that right and light, they have very different content. So probably L and R should belong to different phoneme. So I mean, whether what is learned from self-supervised learning is similar to humans' mind map, it depends on how the model is trained. I believe in today's approach, for example, just consider the masking. It do not consider a wide range of the whole utterance. Probably L and R is not discriminable. It's not discriminate. But in the future, if we found a better way to consider the longer context, more semantic information, probably it will be closer to humans' mind map. I hope this answers your question more or less a little bit. Isn't that context-dependent segregation, right via slide? Yes, it's context-dependent, right? So if you can consider more context information, you can discriminate these two words. But if you only consider the signal, it's not easy to discriminate these two words. I hope this more or less answer your question a little bit. Yeah, you have a very good question, but I do not really have a very good answer. But I hope more or less this inspire you a little bit. You can do more research in the future. Yeah, actually, what is learned from today's self-supervised model? What is the relation of today's self-supervised model with what humans learn is still unclear. This is definitely something you can do more in investigation in the future, because the idea of self-supervised learning are just applied in the recent years, so there's still lots of different things which is unknown yet. Okay, so let's talk about meta-learning. Hopefully we can share with you the basic idea of meta-learning today. So the next topic I would like to talk about is meta-learning and how to apply that to human language processing. Okay, so what is meta-learning? What does meta-learning mean? Meta-learning is learn to learn. So in typical machine learning, you can consider that a developer invent a learning algorithm, and the machine has this learning algorithm, so it can learn from data. For meta-learning, to make the long story short, you can consider it in this way. The learning algorithm is invented by another machine. The learning algorithm is invented by another model. And what the developer do is the developer write the meta-learning algorithm. And because due to the meta-learning algorithm, machine can learn the learning algorithm from the data. After it learns the learning algorithm, it can apply the learning algorithm in machine learning problem. So you can solve machine learning tasks more efficiently with the invented, with the learned learning algorithm. So this is the basic idea of meta-learning. And to be more specific, let's talk about the basic, let's talk about more about meta-learning. So this is the outline of today's talk. I will first give an introduction of meta-learning, then I will compare the difference between meta-learning and machine learning. Then we will go detail through a specific meta-learning approach called MEMO, and we will see how MEMO is applied to human language processing. So let's start from the introduction of meta-learning. Before we introduce meta-learning, I have to review machine learning. And I believe all of you are already very familiar with machine learning, but I have to review it again so we can compare machine learning and meta-learning. Then what do we do in machine learning? As you know, machine learning can be considered as looking for a function. So if you want to do image recognition, you want to find a function, which input is an image, output is the class. Then there are 3 steps in machine learning. The first step is you have to determine what is learnable. So if you want to apply deep learning, you have a neural network and you determine the neural network architecture. So the architecture is not learnable, but the weights and pairs of neurons, they are learnable. In this talk, I use theta to represent the learnable parameters. And those learnable parameters are going to be learned from the data. Then how can we find this learnable parameter? It is still in this way. You have you have to define a loss function. Here I use L of theta to represent the loss function. And usually you calculate the loss in this way. You have some training example, and you have ground truth label for the training example, and you have a model whose parameter is theta. Then you want to evaluate the loss function. You want to know the loss of this parameter. You want to know the loss of theta. So you apply f theta to those training example and obtain your prediction. Then you compute the cross entropy between the model prediction and the ground truth. Then you average the cross entropy, and this is the loss. And this is the loss you want to minimize. Then after you have defined the loss function, then you are going to do the optimization. In the optimization stage, you want to find a set of parameters theta, which can minimize the loss function. We use theta hat here to represent the optimal parameters. Then usually you do it by gradient descent in deep learning. And after you have theta hat, then you use theta hat as your parameter to do whatever you want to do. You use f theta hat in testing. Oh, I believe you're already familiar with all of this. Then let's quickly move to meta learning. What are we going to do in meta learning? We can consider machine learning in this way. We have a learning algorithm, which is capital F. And learning algorithm is also a function. Why do I say that? Your learning algorithm takes training example as input and output the learned model. What we want to do is, for example, image classification, or you simply want to build a cat and dog classifier, then your learning algorithm is a function which takes training example as input and output the classifier, output the learned classifier. So the input is training example, the output is the learned classifier. And this classifier can be considered as learning from the data. However, in typical machine learning, the learning algorithm is handcrafted. Now, what we want to consider in meta learning is this learning algorithm, is the capital F also learnable? Instead of using a handcrafted capital F, can we learn this capital F? This is what we want to do in meta learning. And to find this function, we can follow the same 3 steps in machine learning. In machine learning, we use 3 steps to find a function. Here in meta learning, we can apply exactly the same 3 steps to find this learning algorithm. So let's go through the 3 steps. The first step is determine what is learnable in a learning algorithm. So in machine learning, you determine what is learnable in your model. For example, you want to learn weights and bias of all the neurons. How about learning algorithm? What do we want to learn in a learning algorithm? For example, let's consider deep learning. In deep learning, the parameters are learned from the data. However, there are lots of different components which are handcrafted. For example, your network architecture, your initial parameter, your optimizer, they are handcrafted. Can we learn those components? Is those components learnable? In meta learning, what we are going to do is to learn those components which is determined handcrafted before. And let's consider phi as the learnable component. So here we will represent a learning algorithm as f phi to show that there are component phi in this learning algorithm, and this phi is learned from the data. And there are lots of different meta learning approaches, and each approach try to learn different components. This is first step. Then let's move to the second step. In the second step, we have to define a loss function. Okay, we have to define a loss function. We use capital L to represent this loss function. And this is the loss function. It's not never parameter set. The input of this loss function is fine. The component you want to learn in the learning algorithm. So we want to use this loss function to evaluate how good a learning algorithm is. Then the problem is how to evaluate the goodness of a learning algorithm. The idea is very intuitive. You try to apply the learning algorithm to see how good they are. But to truly apply the learning algorithm, you need to have some tasks to be solved. So to learn the learning algorithm, you have to prepare some training tasks. This task is what you want to, so you use this task to learn your learning algorithm. This is not a task you really want to solve, but you try to use this task to learn the learning algorithm. You try to use this task to know a learning algorithm is good or not. For example, let's say what you really want to do is dog and cat classification. Then you collect some training tasks. Task 1 is apple and orange classification. Task 2 is car and bike classification. All of them are binary classification. And in each task, you have some training data and testing data. In each task, you have some training data and some testing data. These are training tasks. After you have the training task, you can apply your learning algorithm, which is parameterized by find here. You can apply your learning algorithm on each task to know how good the algorithm is. So let's say you take task 1, and task 1 has some training example, and your F5 take the training example as input, and probably you do some gradient descent. So this F5 do the gradient descent, and you have a learn classifier F theta1 hat. Then if this theta1 hat is good, if this theta1 hat is the parameter of the classifier learned from the learning algorithm using the training example of task 1. If this parameter is good, if this classifier is good, then means your learning algorithm is good, then this learning algorithm should have smaller capital L, should have smaller loss. And on the other hand, if the classifier is poor, means learning algorithm is poor, then you have larger capital L. Then the problem is, how can we know a classifier is good or bad? This is simple. Just evaluate your classifier on some testing data. So this is what you do in meta learning. You have this learn classifier F theta hat 1. Then you have some testing example for task 1. So you use the testing example to evaluate this F theta1 hat. So you use F theta1 hat to do the inference on the testing example and obtain the prediction. Then you compute the difference between the prediction and the label of the testing data. Then you compute the difference, you compute the cross entropy between the prediction result and the ground truth of the testing data, then you obtain L1. And the idea is very simple. Here, I try to specify the whole process. You have ground truth for your testing example. You have testing data. Then you use F theta hat 1 to classify those testing data and obtain the prediction result. Then you compute the cross entropy. Then you sum the cross entropy to get the difference L1 here. Then you use this L1 to evaluate how good this F theta1 hat is. And if this L1 is small, that means F theta1 hat is good, means your learning algorithm is good. On the other hand, if the difference is large, the prediction is poor, the prediction is very different from the ground truth, then you have a poor classifier and you have a poor learning algorithm. And only consider one task is not sufficient. You have to evaluate your learning algorithm on many different tasks. So you also take out your task 2. Then the task 2 is bike and car classification. Then you have F5 you use F5 and your training data to obtain a classifier F set ahead 2. You have testing example for task 2, and you use the testing example task 2 to evaluate F set ahead 2. You compute the difference between prediction and the ground truth. Then you have L2. Then you sum over L1 and L2 to form your capital L to represent how good a learning algorithm is. And usually you have many different tasks, so you summation over all the different tasks. Here, capital N means the number of training tasks. You have to collect a large amount of training tasks to evaluate how good an algorithm is, to evaluate how good find is, to evaluate how good capital F find here is. Okay, so this is step 2. And there's something you have to keep in mind. In typical machine learning, you compute the loss based on your training example, right? So I believe you are already familiar with typical machine learning algorithm. So you compute the loss based on the training example. If you have listened to what I say carefully, you found that we compute the loss based on the testing example in a task. We use the testing example in a task to compute the loss. You may be very surprised at the first glance. So, wait a minute. You use testing example during training? Isn't it cheating? You cannot use testing example during training. This is considered as cheating, but it is not a cheating in meta-learning because this testing example are from training tasks. If this is the first time you learn meta-learning, I believe you already feel a little bit confused because you have a training task. And in the training task, you have both training example and testing example. I know this sounds very tricky. I will try to compare meta-learning and machine learning later, and hopefully this can help you understand meta-learning better. But at this moment, if you feel a little bit confused, this is normal. Everyone feel confused first time they learn meta-learning. Okay, so we already talked about first step and the second step. Now let's move to step 3. In step 3, you want to find a learning algorithm which minimize the loss function, which minimize capital L. And so the idea is very naive, just find and find which can minimize this loss function. And you can write down your formulation, your optimization problem in this way. You have capital L to find. You want to find, which is find head here. You want to find head, which can minimize capital L to find. But in practice, it is not that easy to deal with this optimization problem. If you know how to compute the gradient of capital L with respect to find, then it is fine. Just use gradient descent. You can use gradient descent to minimize capital L. On the other hand, if capital L of find is not differentiable with respect to find, then you have some trouble. Usually, you can use other optimization approach to solve this optimization problem. Some people will use reinforcement learning or evolutionary algorithm to try to find a find which can minimize capital L. Anyway, let's just assume that you have some super powerful optimization approach that can solve this optimization problem, and you have find head which can minimize capital L. Now, we are done. We have a learning algorithm, which is capital F find head. So this learning algorithm is parameterized by find head. Then after we have this learning algorithm, sounds a little bit tricky. We have a learning algorithm. After we have some training task, and based on the training task, we have a learning algorithm, then we can start to use this learning algorithm. So you have a testing task, which is dog and cat classification. And this testing test is something you really care about. It's the problem you really want to solve. And this training test, they do not really have to be related to the testing test. For example, your testing test is a binary classification problem. Your training test is just find other binary classification problem as your training test is good enough. They do not have to be related with cat and dog classification. They can be any other binary classification test. Okay, so in the testing test, you have training data and testing data. You use your training data as the input of the learning algorithm F5 head. Then this learning algorithm output a classifier F set ahead, and you can use F set ahead to classify the testing example, and hopefully you can get some good results. And this is the whole framework of meta learning. And why we need meta learning? Because usually, probably the test you really care about only have very little training data. And with very little training data, typical machine learning algorithm may not work well. So this is why we want a learned learning algorithm. And hopefully the learned learning algorithm can achieve good performance with only little bit label data. Hope that the learned learning algorithm is very powerful. You only need little data to achieve good results. And you can find that, so for little data means few shot learning. So you can find that if you go through the benchmark of the few shot learning, usually the state of the art is achieved by meta learning today. So actually lots of people consider few shot learning is equivalent to meta learning, but I disagree. In my point of view, you can consider few shot learning as a goal. If you can use little data to train a model, this is few shot learning. It is not necessary use meta learning. But today, you can find that if you want to achieve state-of-the-art performance on those few shot learning benchmark, usually people try meta learning. So meta learning is widely used to achieve few shot learning. But I still consider them differently. Few shot learning is your goal. It is not necessary to do few shot learning by meta learning. There are other ways to achieve few shot learning. And meta learning is an approach to achieve few shot learning. You can use meta learning to achieve other goals. It is not necessary to apply in few shot learning. You can achieve meta learning in to achieve other goals, but meta learning is widely used in few shot learning today. This is why lots of people consider few shot learning and meta learning, they are equivalent. Okay, so we are going to move to the comparison between meta learning and typical machine learning. So any question from the audience? If you have any question, feel free to leave your question in the chat room and I can see it immediately during the talk. Okay, any question from the audience? Okay, if not, I will move forward. Okay, here we have one. Okay, we have a very good question from Manish. How does this compare to transfer learning? What is the relationship between meta learning and transfer learning? In my point of view, I will consider transfer learning as a larger framework. So transfer learning is you train on some task and hopefully the knowledge can be transferred to other tasks. So in meta learning, you learn something from the training task. And what you learn is the learning algorithm. What is transferred is how to solve the problem. What is transferred is the parameter of in the learning component. So you also transfer some knowledge to the testing task. So I will consider meta learning as one type of transfer learning, but you have other ways to achieve transfer learning, not necessarily meta learning. Yes, this is Oscar as another good question. are we just transferring the data hungry from this task to other tasks from a same distribution? You can consider in this way, meta-learning is also data hungry. But let's consider a scenario. Let's say you want to do speech recognition. And do you know how many languages in the world? There are more than 7,000 languages in the world. So if for all the languages, you have to collect a large amount of label data, it's not efficient. But on the other hand, there are already several languages which is widely used. We already have a large amount of label data. And Google's speech API can already recognize more than 120 different languages. So on those high resource languages, they are not data hungry. We already have some training data. So how about we use those 120 languages to find a good learning algorithm, to find a learning algorithm which is suitable to learn human language, then apply that on the rest 6,900 languages which are low resources. So meta learning is still data hungry, but hopefully with the data we already have, we can make the data hungry not an issue in the future. I hope this answered the question of Oscar. Okay, so here we have a question. Can you give an intuition of why the training tasks don't need to be related to the main task? Yes, this is also a good question. Why we train on bike and car classification can be applied to dog and cat classification. Let me answer this question in another way. Consider optimization. As you know, there are lots of different gradient descent approach. For example, you have Adagram, you have Eden, you have Eden W, you have all kinds of different optimizer. And you can find that usually some optimizer are pretty general. For example, Eden is kind of a default optimizer. And this optimizer can be used in many different tasks. You use Eden in image classification. You also use Eden in speech recognition. So this is something general across all the different tasks. So you can imagine that if what you want to learn from the training task is the optimizer, and this learn optimizer, because optimizer can be generalized to many different tasks. This learn optimizer probably can also apply to very different tasks. So actually, for some concrete example, people do really try to say, we learn an optimizer on, for example, image processing. And we apply this optimizer on very different tasks, for example, translation. Does it work better than the baseline? Yes. There are some literature show that you can learn a good optimizer that can apply to new tasks you have never seen before during the training. I hope this answers Alessandro's question. Okay, thank you very much for all the good questions. Let's move forward. Okay, we have another very long question here. Alessandro say, I'm thinking though that if you have sufficient data, the parameter of an optimizer for one binary classification task would be different to those of other binary classification tasks. Does this work because you have multiple training tasks that somewhat average out the parameters? Let me read your question again. I do not completely understand it. The parameter. Okay, I got it. Yes, I got your question. So you found that if we only learn the optimizer from one task, it probably do not generalize to other tasks. So we need, yes, you need a large amount of tasks to learn a good optimizer, or in general, learn a good learning algorithm. So in meta learning, the number of task become an issue. In meta-learning, in typical machine learning, you say you need more and more training data. So your unit is training example. In meta-learning, your unit is task. You need sufficient task to learn your model. You need sufficient task to make your learning algorithm can generalize to new tasks. So in meta-learning, now you still have the issue of overfitting. So all the theory you learn from machine learning can be applied to meta-learning. You also have the issue of you also have the issue of overfitting. You only have very little task. And people do try to do task augmentation. As you know, in typical machine learning, for example, in image processing, you do data augmentation. You flip your image. In meta-learning, you will do task augmentation. So you can have sufficient tasks to train a generalized learning algorithm. I hope this answered Alessandro's question. Okay, so let's move to the comparison of meta-learning and machine learning so you can have a better idea of the difference between meta-learning and machine learning. Okay, so first let's talk about the goal of machine learning. The machine learning's goal is to find where's my pointer? Oh, it's here. To find a good function. And the goal of meta-learning is to find a function capital F, and this capital F can find another function which is small f. So in meta-learning, you have a capital F, which is your learning algorithm. Capital F take the training data as input and output the function small f. And hopefully you can use this small f in the application you want to solve. This is the goal of meta-learning. Then let's consider the training data you use. In machine learning, your training data are all from one task. So if you want to do dog and cat classification, you collect some data of cat, collect some data of dog, and you try to find some people to label the image for you. This is machine learning. In meta-learning, what you need is some training tasks. You have to try to collect some training tasks so you can find a learning algorithm. And in each task, you need to prepare training data and testing data. And because now it sounds very confusing, you have some training tasks, and in training tasks, you have training data and testing data. Then some people will be very confused when you say training data. You refer to training task, or you refer to the training example in a training task. So it sounds very confusing. So in some literature, we do not call those training data because it would make people confused. So in the literature, many people call the training data here as support set, and the testing example here as query set. So in each task, you have support set and query set. They are actually training examples and testing example for a task. So this is the data you need to collect it in meta-learning. And in machine learning, you have a handcrafted learning algorithm, take training data as input and output a model, which is learned. For meta-learning, you collect a set of training tasks, and based on the training task, you have a learning algorithm. And because to find this learning algorithm, you need a large amount of different tasks. So I call the process of the learning algorithm as a cross-task training. Yeah, because when I usually feel very confused when I discuss meta-learning technology with my students or other colleagues, because when you say training, what do you mean by training in meta-learning in the context of meta-learning? It can be two things. It can be learn the learning algorithm, or after you have the learn the learning algorithm, you try to learn a classifier. So to do the disambiguity, I call the process of find the learning algorithm as a cross-task training. It's not a typical training. It's a cross-task training because it involves a large amount of different tasks. So the typical training in machine learning, I call it within task training. Manage as a question, does meta-learning reduce the data requirements of deep learning overall across the board? I have to say for all the data you use, probably you do not reduce the all data you use, but you reduce the data needed for a specific task. So I hope you get my meaning. So as the example I mentioned, you already have some data for 100 different languages. Hopefully you can find a learning algorithm. Then in the future, other language only have little data. For example, in Taiwan, many people speak Taiwanese Hokkien, and we have only very little label data for Taiwanese Hokkien. And perhaps if a good learning algorithm, we only need little data to train a Taiwanese Hokkien speech recognizer. So we reduce the data requirement for Taiwanese Hokkien. Probably we do not reduce the data requirement for all the process, but we reduce the data requirement for a specific task. I hope this answers your question. Okay, so let's move on to the training process. So in machine learning, you have some training example, and you use the training example to obtain a classifier, and you can evaluate your classifier. And in meta learning, you have some training tasks to find a learning algorithm, and you have how you evaluate the learning algorithm. If you have a testing task and you have some training example, and the learning algorithm can find a classifier based on the training example, then you have testing example for a testing task, and you use the testing task to evaluate the classifier, and hopefully you can get some good results. So this is the framework of machine learning, and this is the framework of meta learning. And in meta learning, when you want to evaluate your learning algorithm, you need to do training, then do the testing. So I call the testing in meta learning as a cross-task testing. So when you want to evaluate a learning algorithm, you do a cross-task testing. In a cross-task testing, we have a training and a testing. So different from typical machine learning, you evaluate how good a classifier is, you just do the testing. But to evaluate how good a learning algorithm is, you have to do the training first, then you have to do the testing. Then let's talk about the loss function. In the loss function of machine learning, you sum over the cross entropy of all the example. In meta learning, you sum over all the training tasks. And in each training task, you have to compute the average cross entropy of the testing example. So here, the small l is actually the small l here. You have your loss for each task, and you sum over the loss of a wide range of different training tasks, and you obtain the capital L. And capital L is something you truly want to minimize. And let's talk about the training process. Usually in the training process, you have to compute the loss. To compute this capital L, you have to compute the small l. To compute the small l, well, it is very computationally intensive. To compute the small l, you have to do within task training first. You have to use the training data of a specific task and use your training algorithm to obtain a classifier. Then you do the testing to obtain this small l here. So to compute the loss of one task, you need to do within task training once and within task testing once. And usually in your optimization algorithm, you have to compute this task, you have to compute this capital L many times. And so in a cross-task training, we need to do within task training and within task testing several times. In some literature, the cross-task training will be called outer loop, and the within task training will be called inner loop. This is because in one outer loop, in a cross-task training, you need to do within task training many times. So within task training is a smaller training in a bigger training. So we call a cross-task training, so some literature call a cross-task training outer loop, and within task training inner loop. So in typical machine learning, you do within task training once and within task testing once. In the whole scenario of meta learning, you do a cross-task training, and in a cross-task training, you will do within task training and within task testing repeatedly. You will repeat this process many times. Then you have to do a cross-task testing. In the cross-task testing, you do within task training once and within task testing once. So this is meta learning, much more sophisticated and computationally intensive than typical machine learning. And one within task training plus one within task testing is called one episode. So in the literature, you usually see some people say one episode. This means one within task training plus one within task testing. So in meta learning, to deal with a cross-task training, you have to go through many episodes. You have to run several episodes repeatedly to find a learning algorithm, and you evaluate on the testing task with one episode. So this is meta learning. If this is the first time you learn meta learning, probably this sounds very crazy to you. So I would like to give you a specific example to show you how meta learning really works. The technology I would like to share with you here is learning to initialize, and it is actually widely applied in several different applications. And among all the learning to initialize algorithms, the most well-known one is model agnostic meta learning, or MAML. And it sounds like mammal. So lots of there's another technique called reptile. So in learning to initialize, you have mammals and you also have reptile. And mammal is developed by Josephine in ICNL 2017. Okay, so in mammal, what is learnable? In mammal, what you like to learn is the initialized parameter. Let's first consider the whole process of gradient descent. So in gradient descent, you first design your network architecture and you initialize your parameter, which is set at 0 here. Then you sample a batch from your training data, compute the gradient, then you update your parameter once and set apply. Then you sample another batch, and then you update your parameter again, then you update set a double point. And you will update your models many times until you are happy. Then in the memo, what is learnable is theta 0, the initialized parameter here. So here in memo, our theta 0 is our fine. In memo, fine is the initialized parameter. So as I have mentioned many times, the step 1 is to decide what is learnable, and fine is the learnable parameter. And in memo, initialized parameter, which is set at 0 here, is the fine we are going to apply. It is the fine we are going to learn by meta learning algorithm. And for loss function, this is nothing different from what we just talked about. So you just calculate the loss for each task and sum over all the tasks, then you got 10 capital L. Then for the training part, is a little bit tricky. For the training part, you want to minimize this capital L. You have to compute the gradient of capital L with respect to phi, and with this gradient, you can update the phi. You can update the initial parameter phi. You can update the parameter you want to learn. And you also need a learning rate here. So you also need to times your gradient with the learning rate and update the parameters. And this process is the outer loop in memo, or it is the across task training. And to compute this capital L, it can be very tricky. It can be very computationally intensive. I'm not going to go through all the detail here due to time limitation, but you can imagine that it's not very easy to compute this term. Even though even though capital L is differentiable with respect to phi, to compute this term is very computationally intensive. Theoretically, is computable, but consider the computational issue is probably intractable. So there are several ways to try to simplify the whole process. The most widely used way is reduce the parameter update steps. Usually in a typical gradient descent algorithm, you have to update your parameter hundreds of thousands of times to get the result. But in memo, usually you assume that you can only do one step update. You only update your initialized parameter once, then the whole training process is done. This is to save the computation. Some people may ask, wouldn't you obtain very poor performance with only one step update? In memo probably is fine because usually memo is applied in future learning scenario. In future learning scenario, you only have very little training data. With very little training data, update many times probably is not a good idea because you may overfit on the very little training data set. So probably one step update is fine for meta learning in the future learning scenario. Of course, if you can develop some way to update the parameter more times with not intractable computation, then this would be a good idea. So people try to do it. One way is do some first order approximation. I'm not going to go through the detail here. You just keep in mind that there's some approach called FO memo. There are some approach called reptile. What they try to do is first order approximation. And there's another very clever way called IMemo, because only update the parameter once doesn't seem to be right. And IMemo is one very clever way that you can update your parameter until convert. You can update the parameter as many times as you like, but do not make the computation intractable. And we do not have time to go through the detail, but you can read the paper IMemo here to learn how to achieve that. I know there's another more fundamental question. Memo learns the initial parameter, but don't forget that memo learns the initial parameters by gradient descent. To apply gradient descent, you also need another initialization. So you need the initialization of the initialization to learn phi. You also need the initialization parameter of phi, which is phi 0 here. So it is turtles all the way down. We want to learn to initialize, but we also need learn to initialize. Or probably we also need learn to initialize. So this is turtles all the way down. And we are going to see how people really deal with this problem in the practical application. We still have 20 minutes. So if you have any question, feel free to type your question in the chat room. If not, the next topic is how to apply memo to human language processing. And I will talk about how in human language processing, in natural language processing, how most people initialize the meta-learning algorithm. Okay, so you can type your question anytime during the talk. I can see your question immediately. So while people are thinking about your question, let's move forward to how meta-learning is used in human language processing. Okay, so here, probably you have a question. Memo is to use to find a good initialized parameter, right? And we just talked about another approach to find a good initialization, which is BERT, right? BERT is also one way to apply. BERT is also one way to find the initialized parameter for downstream tasks, and BERT is widely applied. If we already have BERT, we already have self-supervised learning, do we still need learning to initialize? I will try to answer this question after a few minutes. Another question is, please keep in mind that there is some constraint for learning to initialize approach. There is some constraint for memo. In memo, a basic assumption is all the tasks must use the same model architecture. If some task needs some specialized network architecture, then learning to initialize cannot apply, because learning to initialize is to learn the initialized parameter. So you have to assume that all the different tasks has the same model architecture. In this way, the initialized parameter learned from some tasks can be applied on other set of tasks. So there's some constraint for learning to initialize. You have to assume all the different tasks can be solved by the same model architecture. Can all the different tasks solved by the same model architecture? Let's consider the model input. So probably different tasks refer to different languages. For example, some tasks are for English, some tasks are for Chinese. In this case, can we have the same encoder for all the different inputs? This is possible. We just mentioned multilingual BERT last week, and you can apply multilingual BERT here. So even though your data are from different languages, you can apply the same encoder to encode the input from different languages. But how about the output? What if some tasks have two classes, it's binary classified, and some tasks has 4 classes? Then we need different model architecture. At least you need different tasks to deal different number of tasks, to deal different number of classes. So in this case, if some tasks are 2-class classification problem and some tasks are 4-class classification problem, how can we deal with this situation? This is the second question. And before we answer the 2 questions, I would like to share with you how meta-learning is used in natural language processing. Because I know if this is the first time you learn meta-learning, this idea sounds pretty crazy for you. Does it really work in more realistic application? Does it really work in natural language processing, which usually need a sophisticated model? Let's first take a look about the paper publication. So you can find that in the past few years, the papers related to meta-learning growth. There are more and more papers related to meta-learning. And for the statistic of 2021, I have not included ENNLP and interspeech yet. As you know, ENNLP is last week, so I still do not get a chance to go through the paper. So we can expect that this year, 2021, we can see more paper about meta-learning. So it looks like in the natural language processing community, this idea is become more and more popular. Then let's take a look about what is the algorithm people use. I only consider learning to initialize here. Actually, there are more papers not use learning to initialize algorithm, but I only consider the paper about learning to initialize here. And you can find that more than 50% of the paper apply the original memo, and other paper also explore some approximation approach like FO memo and reptile. Then let's take a look about which application can apply meta-learning. Meta-learning have been applied on machine learning, and even though you are not working on machine learning, it's fine. It's very easy to understand how machine learning works because today people just use end-to-end model. So you train a sequence-to-sequence model, take the token from one language as input and output the token of another language. And to apply machine translation in meta-learning, this is the setup. You can consider some language pairs as training tasks and other language pairs as testing tasks. You can consider the data from some domains as training tasks and the data from other domains as testing tasks. You can consider and this idea, meta-learning, also apply on unsupervised machine translation. And we do not have time to go through it. You can read this paper to see how meta-learning apply on unsupervised machine translation. And it can apply on parsing. And even though you never work on parsing, it's fine. It's very easy to understand how state-of-the-art parsing work because it usually works in this way. So you have a parser. It's actually a sequence-to-sequence model. This sequence-to-sequence model take a token sequence as input and directly output a parsing tree. The parsing tree can also be represented as a sequence. So you can output a sequence, represent the parsing tree. This is usually how you train your parser. And you can apply meta-learning. So you can say, I learn the initialized parameter for parsers on some languages, and hopefully we can find a set of good parameter for new language with little data for from some domain and testing tests for other domains with little data. And this idea can also be applied on dialogue state tracking. And dialogue state tracking can also be a sequence-to-sequence model, can also be an end-to-end model. There are many dialogue state tracking models which are end-to-end. Here I just list some of them. And you can also apply the meta-learning on dialogue state tracking. So you can consider some domain as training tasks, other domains as your testing tasks. And the idea also have been applied on end-to-end test-oriented dialogue and end-to-end chatbot. I just list some reference here. Okay, here we have a good question. Why BERT need to use self-supervised approach to learn parameter? Isn't it apply memo on group generalized to new tasks? This is a very good question. And this is the question I'm going to answer in the next few slides. Actually, BERT, self-supervised learning, and memo, they are not conflict. They are complementary to each other. You can apply BERT and memo at the same time. I will answer your question after a few slides. So just wait for a while. Okay, you can apply this idea on machine translation. You can say, consider some language form the training task and some language form the testing task. And there are other scenarios you can apply speech recognition. And there are more reference, large amount of reference. So let's skip this part and get down to the business. Okay, so question 1. We already have BERT. Do we need memo? Or we already have memo. Do we need BERT? Actually, they are complementary to each other. If you read the literature about applying learning to initialize on natural language processing, you can find that usually people use BERT to initialize memo. Because if you want to train a memo, you want to learn an initialized parameter, you also need the initialization of the initialized parameter. To learn find by gradient descent, you also need find 0. Then where does find 0 come from? You can find that lots of papers consider BERT as find 0. So you use BERT to initialize your parameter. Then you use memo to fine-tune the find 0. Hopefully you can get even better performance than simply apply self-supervised learning. So you can consider that memo is the first turtle and BERT is the turtle under the memo. And I go through the literature, apply learning to initialize, and I found that actually around 50% of the paper today, they will use BERT model to initialize their memo. And I have some example here from the literature. For example, this paper, they are working on parsing. Okay, they are working on parsing. So the horizontal axis, the vertical axis is simply the accuracy of parsing, and horizontal axis are the number of training samples. Actually, it is SPIS, but it's not important. I'm not going to describe what SPIS is here. Just consider it as the number of training samples. And the blue curve is the result of BART. Remember that? We have talked about BART last Friday. BART is a pre-trained sequence-to-sequence model, and so it can be used to initialize a parser. As I say, parser is a sequence-to-sequence model today. Then if you further apply reptile here, a variant of memo, which can be trained faster. If you apply reptile here, you can find that the green curve is the result of reptile and is better than BART in all the different cases. And if you have little data, the improvement is more significant. This is here we have another example. The blue curve is the result of BERT. And this is the result on a set of classification tasks. And the horizontal axis is the number of training examples. If we only have very little training example for the downstream task, remember that BERT also needs training example in the downstream task. So although training BERT itself is unsupervised, training the downstream task is supervised. So you still need some training example. And for BERT, if you only have very little training example, the performance will be poor. But if you apply reptile, you can boost the performance to the orange line. So even though you only have very little data, if you have a good set of initialized parameters, you can have good performance with only little label data in the downstream task. So learning to initialize and BERT, they can be applied at the same time. So what is the benefit of self-supervised learning? In self-supervised learning, you use unlabeled data, but your learning objective do not consider the downstream task. So usually people say self-supervised objective is not closely related to the downstream task. So there is a learning gap between self-supervised learning and the downstream task. For memo, you truly leverage the training task. When you train the memo, you truly consider the performance on the training task. So you truly know what some downstream tasks look like. So you can use memo to further improve the performance of BERT. And I still have around 5 minutes. And this is something very important I would like to share with you. There's another approach, which is more similar to memo. So which is multitask learning. So in memo, you have some training tasks and you use those training tasks to learn an initialized parameter. And it is very computationally intensive. And now I already described how to apply memo to find the initialized parameter. But there's another more easy way and very typical way to find the initialized parameter. And this approach is actually widely used in the scenario of transfer learning, which is just put all the data together. Just ignore learning to initialize. Just put all the data together and use typical supervised learning algorithm to train the model. Use typical supervised learning algorithm to train from all the different tasks, then use the training result as the initialized parameter. I call this approach multitask learning in this lecture. And hopefully, usually, you also get good performance on the testing test. Then what is the difference between learning to initialize and multitask learning? If we consider the performance, usually in the literature, learning to initialize can achieve better performance than multitask learning. The reason is meta-learning, learning to initialize, consider the fine-tuning stage when trying to learn the initialized parameter. It truly consider the initialized parameter will get good performance on downstream tasks or not. And multitask learning do not consider that. Multitask learning just put all the data together and train from all the data, and it happens to have good performance on the testing test. But I put a question mark here because actually you can find some counterexample. You can find some paper to show that actually multitask learning can achieve the same performance as learning to initialize. On the other hand, learning to initialize has a very critical drawback, which is computationally intensity. And multitask learning is more computationally efficient. And both learning to initialize and multitask learning has pros and cons. How about we combine them together? So you can use multitask learning as the initialization of memo. You do multitask learning here, then you apply learning to initialize. Multitask learning is faster and memo is slower but better. So you use multitask learning to find a better solution, probably close to the solution of memo. Then later on, you apply memo. So now the whole initialization process becomes like this. Self-supervised learning is the first stage. Then you do supervised pre-training from the training task. Then finally, you do learning to initialize. And the advantage of self-supervised learning is it can take the advantage of a large amount of unlabeled data. And supervised pre-training and learn to initialize need the training test. So you need some labeled data. And learning to initialize probably can achieve better performance than supervised pre-training because we consider the fine-tuning stage. So we can have 3 stages for initialization. Is this idea works? Unfortunately, the result is kind of mixed. I find some papers apply this idea, 3-stage idea, and show that the performance improve. But I also find some counterexample to show that actually this stage initialization do not really improve the performance. So this is still something under investigation. Due to time limitation, I believe I cannot go through the rest of the slides, but there's on the last thing I would like to share with you is, okay, oh, wait a minute, I pressed it too many times. So here I collect a set of paper which use meta learning in different tasks related to natural language processing and speech processing. There are many of them, so I cannot even put it in the slide. And I put the link here. So if you want to learn more about meta learning, especially how they are used in natural language processing and speech processing, you can refer to the link below. So this is all I want to share with you with meta learning, about meta learning. Thank you very much. Thank you.